Hello, hi everyone, welcome back to the channel. So today in this video lecture we'll be solving this problem counting Haybales, which is yet another problem of binary search algorithm. So this problem is basically is more inclined towards a contest. So these kind of problems are asked during contests, and we have to figure out that this problem is is solved using binary search. So so in these kind of problems we will be given some scenario and we have to figure out, okay, we have to use binary search algorithm here. So let's solve this problem. Let's read the problem statement. Farmer John has arranged his n hay bales. So there is a farmer who has arranged his n hay bales at various points along one dimensional road. So we have a one dimensional road and farmer has arranged some hay bale. Okay, so this is a typical hay bale. This is what we are calling a hay bale. Now he has arranged n such hay bales over a one dimensional road which runs across his farm. To make sure they are spaced out properly, please help him answer Q queries. Now he has to answer Q queries over these hay bales that he has arranged. So what does the queries ask? Each query asks for the number of hay bales within a specific interval along the road. So for each query will be given an interval L to R. We want to find the number of hay bales which lies in this interval, where L is the starting point, LR and R is the ending point. Okay, the first line contains N and Q, two integers representing the number of total hay bales that we have and the number of queries. The next line contains N integers representing the positions of the hay bales which are present on the road, while the next Q lines, each line containing an interval representing the starting point and an ending point, in which I want to find the number of hay bales. And in the output we just have to print the answer for each query. For each query we just have to print a integer representing the number of hay bales which lies in that range. Okay, so let's better understand this problem statement using an example. So here we have an example. Okay, so these are the hay bales that we have. The hay bales are present at position number 3. So let's plot them on a number line. So this is the road. The very first hay bale is present at location number 2, which is here. Then we have a hay bale at position number 3. Then we have a hay bale at position number 5. Then we have a hay bale at position number 7. Okay, so let's mark these positions. This 2, 3, 5 and 7. Okay, let's ask 6 queries. A farmer asks 6 queries. The first query is 2 to 3. Give me the number of hay bales which lies in this range from 2 to 3. Including these points, the endpoints are included. That means the answer would be 2. Here it is 2. 1 at position number 2 and 1 at position number 3. The next query asks for the number of hay bales from 2 to 4. 4 is here. And we have 2 hay bales again at 2 and 3. 2. Then we ask third query, that is from 2 to 5. And there are 3 hay bales at 2, 3 and 5. So we print 3 for this query. We move to the next query, that is from 2 to 7. The number of hay bales would be at 2, 3, 5 and 7. So the answer is 4. Next query from 4 to 6, that is from here to this point. So 6 is here. How many hay bales are there? Only 1. So we print 1 here. Then the next query from 8 to 10. 8 would lie somewhere here. 10 would be somewhere like here. And we can see there are no hay bales. There is no hay bale on any location from 8 to 10. So we print 0 in this case. So that's what we have to do in this problem. Fine. Given some hay bales over a one-dimensional line, given some intervals represented in the form of Q queries. For each query, give me the number of hay bales which are present in that particular interval. So let's try to solve this problem. Let's think about the solution. Now, one of the ways to solve this problem, let's say we have queries. Let's say take any query, particular query L to R. Start traversing this array. So this is the Haybales array. Start traversing this array. Now, if you encounter any element which lies in this range, then simply count that point. Okay, because we have a Haybale there. So let's take an example. 2 2 3. This is, let's take this interval. Start traversing the array. The first element is 3. Does 3 lies in this range? Yes. Count 1. Move to the next element, 2. Does 2 lies in this range? Yes. Count 1 more. Move to the next element. 7 lies in this range? No. Move to the next element. 5 lies in this range? No. So the answer is 2 for this query. So this is one of the strategy to solve this problem, the naive one. But for this strategy, we have to traverse the entire array for each interval. And now we have q such intervals, and each interval takes an entire traversal of the array, giving me the overall time complexity of q multiplied by n. Now if q goes up to 10 raised to the power 5 and n goes up to 10 raised to the power 5 as well, the time complexity would give me 10 raised to the power 5 multiplied by 10 raised to the power 5, that is 10 raised to the power 10. If our computer performed 10 raised to the power 8 iterations per second, it is going to take 100 seconds to complete this task over these constraints, which is bad. We can't do this. We have to optimize the solution. Let's see how we can do that. Now obviously, since we are solving binary search problems, we have to arrive at binary search somehow. Let's see how we can do that. Now observe that the interval is sorted. That means L is always less than equals to R. So if we sort this array, let's sort it. We have, after sorting, we have 2 3 5 7. Then I will always find L in this array before I find my R. Okay, let's take the same example, 2 and 3. Now if I start traversing this sorted array, I will find 2 first. I will count 1. Then I will find the second element which also lies in this range. I will count 1 more. Then I will check for the third element, and here I am saying that this third element is 5. It lies outside of this range. It exceeds the right limit. It exceeds this 3. That means I will never find any favorable element in this part of the array, because all of the elements will be greater than the R. So I will stop traversing the array right at this point, and this would be my answer. Okay, but this is again going to take the linear time complexity, because in case we have a interval which covers all the points of this array, in that case I will again end up traversing the entire array. So we have to optimize it. Now observe one fact. Observe one fact here. Let's say this is the interval. Let's take the very first observation. I want to find all the elements which are less than or equals to this 6 or R. All elements less than equals to this R. Second, okay, why? Let's say we have 6. Then if I count all the elements which are less than equals to 6, we would have 3 elements. Now the second observation, if I find all the elements which do not exceed 2, if I find all the elements which are less than 2, how would I find that? All elements, find all elements less than L. How many elements are there which are less than this 2 or L? We can see we have 0 elements. Okay, so 0. We don't have any element which is less than 2. So we have 0. If I subtract this 0 from the 3, that would give me 3. And this represents exactly the number of elements which lies in this range. We can see we have 3 elements, 2, 3 and 5, which lies in this range. I found it using these two observations. If I can somehow find all the elements which are less than equals to R and all the elements which are less than L, I would find the elements which lies in this range. Okay, fine. How this is working, let's plot it. We have 2 here, we have 3 here, we have 5 here, we have 7 here, let's say 6 is here. All the elements which are less than equals to 6. Okay, 3 elements. Okay, so what does this represents actually? Let's say, so we have an element R, this one. What I want is, if I find the position of the very first element in the sorted sequence, which is just greater than R, which is just greater than R. Okay, so let's call it J. J is the position of element, the first element in this sorted sequence, which is just greater than this R. Okay, that's what I'm saying in other words. That's how I will find all the elements, the count of elements which are less than or equal to R, because we are using a 0 based indexing. Okay, if I find the position of that element, for instance here, let's say we have this range 2 to 5. I want to find all the elements less than equal to 5, and we have 3 elements, 2, 3 and 5. If I find this, the position of this element, that is 7, which is just greater than this 5, I would get the number of elements which are less than equals to 5. Fine, the position is 3. That's what I'm doing here, and this is nothing but upper bound. Okay, similarly, if I find all the elements which are less than L, this L, this is equivalent to saying that find me the position of the very first element which is not less than L. Fine, so let's say we have 2 here. Now find me the position of the very first element which is either equal to 2 or just greater than 2. So we find this 2, we have this 2 here, so that is what I am going to get, and this is nothing but lower bound. Here I want to find the position of the element which is strictly greater than R. Here I want to find the position of the element which is either greater than R, either greater than L or equal to L. That's all, and the answer would be nothing but, let's say this is I, it would be J minus I. That is upper bound for this right limit and lower bound for this lower limit. The difference would give me the answer for that particular interval. Okay, and we know we have already understood these concepts of upper bound and lower bound in the previous videos. So I hope you understood the logic here. Let's try to implement it. Okay, so this is the implementation of this function we have, which is count Haybales function, which takes in the Haybales array, the queries. Find me the size of the Haybales, the size of the queries array. Sort these Haybales in increasing order. Iterate over each query. Find the endpoints, like for each query we have a starting point, we have an ending point. Now find the lower bound for this starting point, find the upper bound for the ending point, and print the difference. That's all we have to do. Okay, now let's discuss the time and space complexity. You can see that this sorting the Haybales, sorting the array takes n log n. Now come down, this is, we are iterating over q queries. For each query we are performing binary search twice, so we are performing binary search log of n plus log of n, binary search twice, and that would give me overall time complexity of q multiplied by log n. Okay, which is far better than the complexity which we had earlier. While the space complexity is constant, it is constant because I'm not using any extra space to implement the function. Okay, so this is the time complexity q log n, and this is the space complexity. Let's jump to the code implementation part. Okay, so this is the count Haybales. So this is the solution class. We have this count Haybales function, which takes in these Haybales and the queries. We find the size of the Haybales that we have, size of the queries that we have, the number of queries, iterate over the queries, find the upper bound for the right limit, or first find the starting and ending point for this particular query. So we have queries, and now find the upper bound. The upper bound would be upper bound. So before that we have to, I forgot to sort this Haybales array, so we have to sort this as well. Okay, and we have to subtract Haybales dot begin to find the index of this upper bound. Similarly, we find the lower bound, and print the difference ub minus lb. That's all in a new line. So that's the implementation of this count Haybales function in C++. Let's see the implementation in other languages. Now this is the implementation in Java, and this is the implementation in Python language. So that's all for this video. If you like the video, then hit the like button and stay with me in this binary search series. We have a couple of problems remaining, then we'll start another topic, and I hope to see you all in my next video.